Most skyscrapers fight gravity. Tokyo Skytree had to fight gravity, earthquakes, typhoons, soft ground, radio interference, and a problem nobody had ever solved before. When construction began in 2008, Japan was attempting something unprecedented, building a 634-metre freestanding tower in one of the most seismically active urban regions on Earth. Today, Tokyo Skytree remains the tallest tower in Japan and one of the most sophisticated examples of structural engineering ever built. Here's how it's made. Let's start with a simple question. Why build Tokyo Skytree at all? By the early 2000s, Tokyo Tower had a problem. When it opened in 1958, standing at 333 metres, it was more than tall enough for broadcast transmission. But Tokyo had changed. The city kept growing upward. New skyscrapers were beginning to interfere with signals, particularly as digital broadcasting became more important. The obvious answer was to build a taller broadcasting tower, 634 metres tall to be exact. And the engineering reality was a lot more complicated. The team launched weather balloons to measure wind behaviour at altitudes where almost no Japanese structure had ever operated, and at the same time, they carried out extensive geological investigations to understand exactly how the site would respond during an earthquake. One of the biggest challenges was stopping a very tall structure from rocking. Tokyo sits on layers of soft alluvial soil, which for ordinary buildings works totally fine, but for a 634-metre tower, it's a completely different conversation. Any rotation or movement in the foundation gets amplified as you move upward through the structure, and when typhoon winds or earthquakes start pushing on a tower this tall, the forces trying to overturn it become enormous. The solution was a series of massive wall-shaped foundation piles designed to maximise friction with the surrounding soil. Instead of behaving like simple columns buried underground, these piles were designed to grip the earth. Only once engineers were confident that the foundations could control movement could they start thinking about the tower itself. You can't just build a strong tower, you need to build an efficient one, and that starts with the shape. One of the strange realities of structural engineering is that making something stronger can sometimes make things worse. Add enough weight and the earthquake forces increase. Add enough material and construction becomes more difficult. At ground level, Skytree has a triangular footprint, but as it rises, it gradually transforms into a circular form. The lower triangular form provides stability through 3 widely spaced structural legs, and higher up, the circular geometry behaves more efficiently against wind. The transition allows the tower to take advantage of both. Skytree also contains around 37,000 individual steel framework members. Every section has different load requirements, different forces, and different dimensions. Factories across Japan produce these components that were then transported to Tokyo and assembled on site. If you ask structural engineers what makes Tokyo Skytree special, this is usually the first thing they'll mention: the Shinbashira, or the central column. The idea comes from traditional Japanese pagodas. Many historic pagodas contain a central pillar that behaves differently from the structure around it. For centuries, builders noticed that these structures seemed remarkably resilient during earthquakes, and what modern engineers discovered was that the central column wasn't simply supporting the building, but helped control the movement. So when Skytree was designed, engineers borrowed the concept. Right through the centre of the tower runs a reinforced concrete core approximately 8 metres in diameter and around 375 metres tall. Up to about 125 metres above ground, this core is connected directly to the surrounding structure. The central core and the outer steel frame can move independently, linked through oil dampers. The difference in movement helps absorb energy and reduce overall sway. Innovative designs matter only if they work in the real world, and nature provided an opportunity to find out. On March 11, 2011, the Tohoku earthquake struck Japan at a magnitude of 9, one of the most powerful earthquakes ever recorded. At the time, Tokyo Skytree was still under construction, and while this wasn't the kind of test engineers hoped for, it was the kind that reveals whether a design philosophy actually works. And the structure withstood the event and remained standing. Every engineering decision up to that point created a structure capable of operating safely in one of the harshest environments imaginable for a tower of this scale. Tokyo Skytree is often described as the tallest tower in the world, but that's not what makes it remarkable. Lots of structures are tall. Few are forced to solve so many conflicting problems simultaneously. And its most important innovation comes from a concept Japanese builders understood centuries before modern structural dynamics existed.